Okay, so good evening, everyone. And today I am going to talk about how we can measure the speed of gravity and some dispersion relations, which is not omega equal to ck, or the dispersion relation predicted by GR, using just one gravitational wave source in a single cosmic explorer. So, by the way, I am Pratyusava Baral, and I am a PhD student in University of Wisconsin, Milwaukee. Okay, so this is the rough outline of my talk. I will first introduce what Cosmic Explorer is and then talk a bit about how we detect and do parameter estimation of gravitational wave signals. Then I am going to talk about how exactly are we measuring speed of gravity by only using one detector and no electromagnetic counterparts. It's a completely gravitational wave measurement. And then I'm going to introduce the system that we are using for all of this, and then I'll just move on to our results. So first of all, what is Cosmic Explorer? So Cosmic Explorer is a next generation gravitational wave observatory, and it will be operational around mid 2030s. So the plan as of now is to have two gravitational wave detectors, one with arm length 40 kilometers and one with arm length 20 kilometers, and both the plan is to have both in the US and one Einstein telescope with 10-kilometer arms in Europe. However, for what I'm going to discuss today, I'll just use one 40-kilometer cosmic explorer for the study. And this is an artist's impression. It has not been built yet. We don't know where we will get the detector, so it's just a concept. Okay, so for Cosmic Explorer, the thing that happens is the noise curve is given by this blue line, and this orange noise curve is the noise curve for the present LVK run, which is going on. So two things to notice. First of all, Cosmic Explorer is much more sensitive than the detectors that we have today. And also the frequency band that Cosmic Explorer can observe is large, like it's from 5 to a few thousands of hertz. And for the present generation detectors, it's roughly from 20 hertz to a few thousands. And that's very important for what I'm trying to do. And I'll come to it again later. So what does a gravitational wave detector detect? So it's just some amplitude as a function of time, and we have some pre-computed set of templates which are a function of masses and spins, and we match these templates with the amplitude. Okay, so the video is not playing, so this is the amplitude that we have, and we have some pre-computed templates, and we just slide the template over this amplitude and calculate something called the signal to noise ratio, which is given by this expression. This D is the data, H is the template, and S of F is the noise curve that I showed in the previous slide. And then if we get a spike in the signal to noise ratio, then that might be a signal. There are some tests that we do, which I'm not going to be talking about in today's talk. And then we can identify a region which has a signal. And once we have identified a region which has a signal, we move on to estimate what the parameters of the signal is by a process which we call parameter estimation. So what is parameter estimation? The observed chunk of data that we have identified contains both data, the gravitational wave signal, and some noise. So this H is the gravitational wave signal and N is the noise. We assume a noise distribution, that the noise is stationary and Gaussian. What it means is that the noise is drawn from a Gaussian random distribution with mean 0 and standard deviation 1. So if we assume a noise distribution like this, we can define a likelihood function, which is the probability of data given the parameters, and this is just a Gaussian distribution where these brackets mean integral like this, and we can get the probability of data given the parameters. However, we are interested in the parameters. We want to calculate the probability of the various parameters given the data, and by parameters I mean masses, spins, the position, the luminosity distance. It's roughly 10 to 16 parameters, however, like it depends how you want to do it, and we just use Bayes' theorem. So this is the likelihood, this pi is the prior distribution, it's the prior knowledge that we have about the parameters. Like let's say we know that DL has to be a few hundreds of megaparsecs and stuff like that. And this Z is just the integral of the numerator. It's just a normalization constant. We don't need to worry about it too much. So in principle, we can calculate this posterior distribution, but this is hard to compute. Because if you want to do a grid of all these parameters, let's say we have 10 parameters and you choose 100 values of each parameter, then you need to evaluate this 100 to the 10, like 100 to raised to the power of 10 times, and it's not feasible to do that. So that's why we use various sampling techniques, and for my work I use a nested sampler called Dynasty to sample this posterior distribution. I won't exactly go in the details how we do this. And also we had to approximate the likelihood, because this exact likelihood is very expensive to calculate. We use something called relative binning to approximate this likelihood, and that makes the problem more computationally feasible. Okay, so now let's go to the main part of the talk. How do we measure speed of gravity by only using gravitational waves? So presently we have 3 operational detectors, one in Hanford, one in Livingston, and one Virgo detector in Italy. And the gravitational wave that we detect in the detectors is just the 2 polarizations times the antenna patterns, and the antenna patterns depend on this vector n. So this vector n is the vector from the detector to the binary. Now if the detector is located at different places, then this vector n will change, and if the vector n changes, the distance changes, and the time when the gravitational wave will arrive at the detector, that also changes. So let's say if you get a signal in Hanford at time t, at Livingston you will get the same signal, say after 5 milliseconds or some value which is less than 10 milliseconds. So given that we have 3 detectors at 3 different places, the vector n changes, and that actually allows us to measure speed of gravity. And we have measured speed of gravity using, like, the present measurement is, I think, 0.99 plus minus 0.02. Now, definitely our baseline is not very long, so we need multiple events. This is a constant from 50 events, I think, and you can check this paper for more details. But we can do something else. Remember, I said in Cosmic Explorer, the frequency band is from 5 to few thousands of hertz. So the signal will be in band for a much longer time. And as the signal is in band, let's say for 2 hours, the Earth will rotate around 30 degrees. So if the Earth rotates, this vector n actually changes. And as this vector n changes, we get the speed of gravity in the expression. So effectively, what we can say is that each frequency arrives at a different time, and the time at which each frequency arrives is dependent on the speed of gravity. So for Cosmic Explorer, if we have a loud enough signal, like I use a signal of SNR 1000, and the signals that we detect today will easily have SNR of 1000 in Cosmic Explorer. So it's not a very exotic signal in that sense. So this is the first effect that we can use to measure the speed of gravity in Cosmic Explorer using just one gravitational wave event. There is one more effect which Professor Gopakumar was talking about this morning. So if you look at the frequency band of LIGO and the length, like the typical length of the LIGO-Virgo detectors is 3 to 4 kilometers, and calculate this dimensionless quantity FL by C. So that's just the length of the arm divided by the wavelength of the gravitational wave. The number that you get is around 1e minus 2 to 1e minus 3. In Cosmic Explorer, the length of the arm is 10 times more, so this number improves by 1 order of magnitude. And as this number improves by an order of magnitude, what happens is that the wavelength of the gravitational wave, at least in high frequencies, become comparable to the size of a detector arms, and so the photon moves in a variable gravitational field. This is exactly the same effect which Professor Gopakumar was talking about in NANO-Grav, like the math is exactly the same, but I'll quickly go over it. So let's say we have a space-time diagram like this. This is the x arm, which is denoted by vector p, and this horizontal axis is the time axis, and this is a beam split. This is the beam splitter from where the photon leaves at space-time event 0. It reaches the end of the other arm, which is space-time event 1, and then gets deflected back to the downlink journey and comes back to the beam splitter at space-time event 2. We need to calculate the total redshift for this, the downlink and the uplink journey, and it's pretty easy to calculate. Like, we need the waveform or the metric here, the metric here, and the metric here, and once we know the metrics and we have to project appropriately along the arms, we can calculate the redshift for the uplink journey, the redshift for the downlink journey, and finally add them up to get the redshift for the total journey. So this is the expression for the metric in time domain. It's easier to do in the frequency domain, so we just take a Fourier transform, but everything can be done in any domain which you like. And finally, this is the total redshift, which is, this is a redshift due to uplink journey, and this is a redshift due to a downlink journey. And you can just plug the expressions in and do some algebra, and this is the final expression you get, where this d is given by this expression. Note in LIGO, this number FL by C, this tends to 0. So the value of d is 1, and this can be seen in this plot. So if you look at the orange line, this is the LIGO region where FL by C tends to 0, so the magnitude is always 1 and the phase is always 0. But if you look at the region for Cosmic Explorer, you see there is some variation in magnitude and some variation in phase depending on the position of the source. So this also actually gives information where the source is located, and this is the Cosmic Explorer region. If you go for pulsar timing arrays and other detectors, then all like these effects are greatly magnified. So this is the second effect that we are using to measure the speed of gravity. It's not as important as the first effect, but we also need to take this into account. Okay, so what is the source that we are using? So we are using a fictitious source which we call GW370817. It's a GW170817 like event, and way gravitational waves are named, it's first the year, then the month, and then the date. The only difference from 17017 and this event is 17017 has an inclination of 0.2, so it's very face on, but this event is edge on. We do this for two reasons, because first of all, if you have an edge on event, higher modes will have a greater SNR, and I'll explain why. And also the SNR of the injected signal reduces a bit. Like if you have a super high SNR signal, it's very hard to do a parameter estimation. You can think that you need very fine grids to do that, and that's expensive. So first I'll explain what higher order modes are. So in post-Newtonian theory, the gravitational waveform can be decomposed in terms of spherical harmonics. And this is YLM, the inclination and the phase. Now, if the inclination is 0, we only have the 2-2 mode. But for pi by 2, we will have all the modes. And it's easier, like, it's better if we have all modes, because each mode has a different time frequency relation. So it's like roughly, if this is the 2-2 mode, then the 3-3 mode will be a bit different. So if we have multiple modes, it's like having multiple signals from the same source. So the constraints are better if we have higher modes, and that's why we just choose the inclination of the event to be pi/2. Okay, and the time to merger for different modes is also different in post-Newtonian theory. For example, let's say from 10 Hertz, a 2-2 mode lies in band for around half an hour, but for 3-3 mode, it will be for 2 hours, and it will be around 5 hours for a 4-4 mode. So the frequency evolution is different for each and every mode, and that actually helps us in our analysis. Okay, so finally, we move on to the results, but the important thing is how at all we calculate the waveform, and this is this is a bit complicated to do because we need to take into account all these effects in the waveform, and also the waveform has to be somewhat computationally cheap so that we can just sample over this 10 to 12 dimensional parameter space. So a gravitational waveform is given by f plus times this h plus f cross times this h cross. And for parameter estimation, it's easier to work in frequency domain. So we can just calculate this h of t and take the Fourier transform numerically, but that's expensive. We want an analytic expression, but these f plus and f cross functions are complicated that we can't take a direct Fourier transform. So there are several approximations that we can do. The approximation that we do is we assume that these H's oscillate more than the antenna responses, and that's not a very bad approximation. That's more or less true. And in that approximation, we can just take the Fourier transform of the waveforms, which already exists in the literature. We have all these IMR phenom waveforms, which are in frequency domain and are pretty cheap to calculate. So if we take the Fourier transform of the waveforms, we now need the f plus and f cross in the frequency domain. And what we do is we have the time frequency relations. So we just make this time as a function of f. And in that way, we get f plus and f cross as a function of f. Now note this time frequency relation changes for every mode. And so we have to do this calculation mode by mode. So this depends on the azimuthal mode m, like m equal to 2 will have a different relation, m equal to 3 will have a different relation. And this is how we generate our waveform, and we inject the waveform and see how well we can estimate the speed of light. So this is the result that we get. This is how speed of gravity looks like, and this is the this is a 10 parameter Bayesian estimate, and we get using GW370817, we get 1.01 plus minus 0.04 C. If you look at the current constraints, or I took the constraints from this paper, it's 0.99 plus minus 0.02 C using 41 real events. And that actually highlights the power of the next generation detector. By just using one event, you can get a constraint which is similar to what we have today using like 50 to few hundreds of events, which we see. Okay, so now the final part of my talk. So the dispersion relation that I used, omega equal to Vk, that's not very realistic. Like it's very hard to find a theory that will give you a dispersion relation like this. So most dispersion relations have some frequency dependence. Like if you have a massive graviton, then a mass term, and also you can have several other theories which I have listed down here. So we use a phenomenological model where E square is equal to P square C square plus A alpha P alpha C alpha. Here there is no Einstein summation. Alpha can take any of these values. Alpha can't be 2 because if alpha is 2, then we get back the omega equal to Vk relation. So alpha can be 2, alpha can take any of these 8 values, and we can measure A alpha using this dispersion relation. But now we have a problem. We need to know how the waveform looks like in a theory which allows this dispersion relation, and that's a very big problem because all the waveforms that we have are mostly GR waveforms. It's very hard to get a waveform that's not a GR waveform and is very cheap to calculate. So we make some assumptions. We assume that there is no change in the local wave zone. By local wave zone, what I mean is, so if this is the binary and this is the observer, let's say this is the boundary of the local wave zone. So it's far away from the typical length scales of the system, but it's near to the source when you compare to the observer. So we assume that GR is valid in the local wave zone, and this changes only affect in propagation, and also we have like assume that effects are linear in E, and that's mostly true because we know GR is valid up to a very good degree. And if we make these assumptions, we get an effective phase correction, and that's actually a good thing because phase is very well measured in any compact binary signals. So we get a phase correction which we can easily add and check how well we recover these parameters, which is A alpha. So this is the parameter that we introduced for A0. That's just the square root of, that's just the mass square. For A1, A2 you have. And yeah, like this is also done in the TGR group in LIGO. So it's just the same model that we are using. And then these are the constraints for A alpha that we get using this event in one cosmic explorer. Since it's in the frequency, the constraints are very, since it's in the phase, the constraints are very good. And this is the constraints from GW370817. So we get one order of magnitude better constraints, like this is 1e minus 21. This is 1e minus 20 than what we have in GW370817. And also I would like to remind that this is just using one event. So I would end my talk using this. So to conclude that we demonstrate that it's possible to using constraints by just using one event in Cosmic Explorer, which is pretty similar to the constraints that we have currently, and definitely we will have several events in Cosmic Explorer. So the potential of these detectors is huge. And the framework that we have, this can be used to, it's very general and can be used anywhere as long as we can calculate h of f efficiently. This is not public yet, but we will make it public very soon. But there is always one disclaimer or caution, like let's say even in LIGO, we do a measurement and see, we measure the speed of light that's not see something else. We have to be very careful that there is no waveform systematics or astrophysical effects. For example, if we model the rotation of Earth incorrectly, this can come up as a beyond GR effect, but that's just because the waveforms that we are using is incorrect. So a better understanding of these effects is required, and this is primarily future work. Okay, so thank you, and I'll be happy to take questions.
So these are very loud events for Cosmic Explorer. So why do you need to do Bayesian analysis? Fisher information will be more than enough. The reason why I'm asking is that therefore, the fact that during the evolution of that event, the things rotate and all that can be much better modeled into the waveform. And it will not be computationally, expensive. It's and you will not find much of a difference. This has been demonstrated by, earlier papers by Sanjeev Durandar and others. So just curious.
Yes, so the main reason we started doing this is, like, if you look at the earlier papers, they actually use a baseline, and when you use a baseline, you can localize it as one blob in the sky. But if you have only one detector for some sources, you will just get two blobs. And that's a problem. Like if you get two blobs and you do a Fisher information matrix, then what you are doing is you're essentially putting the source in the correct blob. And that can put some errors in the analysis. So even for SNR 1000, for some inclinations and some positions, we see like multimodalities in the location. Now, if we are sure that there will be no multimodality in the sky map, then definitely we can use a Fisher information matrix, and what we get will be exactly the same. Like for my source, there is no multimodality, so we can do a Fisher information matrix.
Yeah, just to make sure that it's consistent and it's much faster, and see how effects of the Earth rotation and all that can be much more cleanly. You made an approximation. Just curious. And the kind of space-time plots you showed, that looks like a lunar ranging kind of measurement. So this is very nice.
Yeah, that's correct. Like if we can ensure that there will be no multimodality, this is exactly same what we will get from Fisher information matrix, and that's much quicker. Like this takes around like 1.5 days to complete. Fisher
Even Dynasty, like, which is much faster than
it's like maybe 1 hour or less than that.
Yeah. Okay.
Yeah, that's correct.
Yeah, thanks.
More questions, comments? If not, then let's thank all the speakers again. And we're done with all the talks. Thank you.